Hey everybody, it's Dr. B here, trying to catch up with some of the lectures. As you're aware, of course, the campus has been closed for the past nearly 2 weeks. Let's give our best wishes and to those folks who've been severely affected by the fires, and I hope that we all can help out somehow. At least keep them in your thoughts during the Thanksgiving holiday. Anyways, I'm going to be posting a couple of lectures. We'll see how it goes. These files are a bit big, and I don't know if I could fully post a 1 hour lecture, but we'll try it. We'll see how it goes. We're going to continue on with the ideas about gastric emptying. Last time, recall, we were talking about gastric emptying of liquids. We're going to continue on describing the gastric emptying of solids, and then get into gastric secretions and injuries and inflammation. And I remember something that I told you about in regards to gastric emptying. And overall, if you think about it, we typically have a gastric emptying rate that is probably no greater than about 200 kilocalories per hour, because it appears that the small intestine can only handle material coming out about that. And if it gets coming out a little bit more than that, well, it's a little hard for the small intestine to deal with. And the problem is that if the small intestine can't absorb it, then it ends up going into the large intestine. It gets fermented. Not a great thing, because it could sometimes lead to severe diarrhea and these presentations that we call malabsorptive disorders. When we last left off describing liquids, I mentioned that there are a couple of parameters that we would consider that affect the emptying rate. Certainly, we want things to come out no greater than 200 kilocalories per hour. But we also noticed that if you were to have something that was isocaloric, and we're just to compare the composition of the liquid, we found that fats basically, if there was a high fat content, that is, if there was a high fat content in the liquid, it tends to empty out slower compared to something that has proteins. And proteins empty out slower compared to something that's like, say, pure carbohydrates. So we saw that there was this compositional issue that arose in there. And finally, we also noted that in regards to, like, say, pH and tonicity, acidic contents tend to empty out slower. Also, high tonicity in the contents tends to make things empty out a lot slower too as well. So let's go ahead and continue on. Let's consider and take a look at our solids and how those things are emptied out. What's pretty remarkable is that when we look at gastric emptying, gravity has no bearing on it. So it doesn't matter about the position of a person. And even if you put them in outer space, gravity really doesn't affect emptying at all. So that's pretty remarkable that this happens in you and me. So let's consider the digestible emptying of, digestible solids, how that empties out. So in general, digestible solids, these guys empty slower than liquids. And what you typically will find in regards to solids, that you'll always see this particular thing that we refer to as a lag phase. And if you remember that we described what happened with the stomach and how it would do all those contractions, I was telling you that there's this so-called fed motor activity, if you remember that. And what happens during the fed motor activity is that we are trying to break apart our food stuff into smaller particles so that they'll eventually be emptied. Recall that things get to be about 1 millimeter in diameter. So what happens during the lag phase, this is where we're basically breaking things down. So you'll break down food particles to roughly about 1 millimeter in diameter before they're finally emptied. And so you can imagine that some food will have a longer lag phase compared to others. So you can imagine it's going to be depending primarily upon the size of the food stuff that's within your stomach. Bigger, of course, that implies that you're going to have a longer lag phase. If you happen to have smaller food particles, obviously you're going to have a shorter lag phase. What's surprising is that if you deliver a foodstuff, a solid foodstuff, in which the size is approximately less than, a quarter of a millimeter in diameter, you pretty much will see no lag phase. Now, do you and I consume any kind of food stuff that's smaller in the diameter, of 0.25? Probably. If you eat, say, applesauce, if you eat, like, say, baby food, things that's really mushed up or blended quite well, typically you will not see anything pardon me, anything of that particular diameter that would be having a lag phase. Now, this is probably the most important thing, is in consideration of the size of the particle, because that obviously will be influencing the lag phase. You could also imagine that if the foodstuff were particularly tough, if there's a lot of connective tissue in the foodstuff and it's hard to break apart, lag phase obviously is going to be longer in duration. You could think of, say, meat that has a lot of connective tissue in the muscle fiber. The harder it is to break down, well, the longer it's going to stay within your tummy. And that's why if you eat something with a lot of meat in it, you probably find that you feel rather full for a longer period of time. It's because, well, your stomach is taking a long period of time to break it apart because of all that connective tissue. Are there anything else that affects the digestible solids, how they empty out? Calorie content, of course. And as you can imagine, the same rule applies, where you have to empty out the contents from the stomach of a rate of no greater than about 200 kilocalories per hour. So that means if you increase the calorie content, that implies that you're going to have a longer lag phase. All right, longer lag phase. Things that don't have very much calories. So you imagine if you were consuming, like, say, I don't know, lettuce or rice cakes. I don't eat rice cakes because, well, they're not delicious to me, but some folks do, and there's not much of a lag phase associated with them. Now, what's strange is that we have to ask our basic question, how is it that the stomach is able to determine the size of the particle? Because if we're going to say that, look, you have to have something that's coming out of the stomach about 1 millimeter in diameter before it finally empties out, the big question, of course, is, well, how is the tummy going to be able to do this? That distal stomach. I'm going to put in my notes over here to the side, see how well this works out. Okay, let's consider this mechanism of gastric emptying. Let's go ahead and draw ourselves out a part of the stomach. We're going to be drawing out pretty much the antral region of the stomach. And what it appears is that the antrum of the stomach somehow can separate out the particle sizes. I apologize for my sloppiness of my handwriting. I'm not so used to writing down in this pad here. But anyways, so let's go ahead and draw our antral region of the stomach. So pyloric sphincter sitting over here. We're going to draw a portion of the duodenum right over here. All right, there we go. And there's our pyloric sphincter. And over here is duodenum. And I'm going to draw the pyloric sphincter partially open. So in the old days, what people used to think is that the key to emptying of particles from the stomach is that it was dependent upon gravity. And remember, I said to you that basically with regards to emptying, gastric emptying, gravity is not a factor. And the reason why it was thought that gravity was a factor was that it was often believed that the stomach was sitting inside of our body kind of looking like this. So if you had the stomach sitting here like this, and the pyloric sphincter was sort of downward over here, the theory was that what will happen is that the tiniest of particles was sitting over here really close to the pyloric sphincter, and then gradually the bigger particles will be then sitting on top of it. So then you'd have the largest particles towards the top of the stomach. This was the old idea, so that the tiny little guys were sitting there right next to that open pyloric sphincter, and that's how you achieved the gastric emptying. The truth is that you can go ahead and have, well, you frankly can have gastric emptying while you're laying down. There's no worry about where you're positioned. It works perfectly fine. So then that's when people figured, well, maybe there's something else that's happening that's influencing gastric emptying. And it turns out that the major important mechanism that's governing this, and I want us to think about it, is basically this idea about fluid dynamics. Now, in general, whenever you take a look at flow of fluids, whether you got this covered in 101 or not, one of the things we should have told you about is that fluids tend to flow in what's referred to as laminar flow. And within the stomach, you can imagine that there's going to be fluid that's basically flowing within the stomach. Even as it does this retropulsion and so on, there's essentially these layers of fluid that flows. And what'll happen is that during laminar flow, you'll have fluid within a center of a column. So imagine that this is three-dimensional like this, right? My hands are supposed to represent the pyloric sphincter, or pylorus, or the antral region of the stomach. In the middle of the stomach, this layer of fluid right over here, this is where you would have the fastest flow of fluid. Then meanwhile, over here in the periphery, this is the place in which you have the slowest flow of fluid. Nice and slow over here. And then as you get more and more towards the middle, it starts to speed up. Then finally you have the fastest flow again in the middle of the pylorus. So what happens during this laminar flow is that what occurs is that you have the smallest particles. These guys will then basically partition to the middle. The reason why is because since they're the tiniest particles, it's easy for them to remain within the very fast moving region, the fastest moving layer, if you will. Whereas the largest particles, those tend to remain within the periphery. And the reason why they remain in the periphery is because, well, the flow is slow over here, and the big particles just preferentially tend to end up more in the peripheral region. So it looks kind of like this. So I'm going to exaggerate this. You have these really big particles of foodstuff sort of sitting out here in the periphery, like this. So there's our big particles sitting over there as such. And then as we get more towards the middle of our fluid column, the particle sizes get smaller as well. So smaller particles as we get more towards the middle, like this. And then finally we get our tiniest particles that are sitting right over here in the middle of the fluid column, sitting in there like that. See that? Largest particles over here in the periphery, smallest in the middle. And as a result of that, the smallest particles are lined up exactly where the opening of the pyloric sphincter is. And so as a result, that is how you get the tiniest of the particles that could get emptied out, because they're situated right where the opening of the pyloric sphincter is. This fluid dynamic type of model seems reasonable, and it kind of makes sense because after all, that's exactly how fluids will behave. Now, some would say, it's a different type of a fluid. It's not really a Newtonian fluid, but look, the velocity is slow enough here that it does behave with Newtonian mechanics, and so this kind of rule does apply, where you'd have, again, the tiniest particles sitting in the center of the column. They could then empty out because they're right situated at the opening of the pyloric sphincter. And meanwhile, these big old particles are sitting out here in the periphery, and then they could be mixed up, and then eventually they could shoot out after they've been broken apart a little bit more. So this is the idea, how you and I managed to do this gastric emptying. All right, it's all a matter of this fluid dynamics. Last but not least, I'm going to separate this all out. We're talking about liquids. Here we're considering solids. Fats. How do fats empty out? Well, what's weird about fats is that in comparison to solids and liquids, remember, liquids tend to empty out faster compared to solids, and we're assuming that they all have the same caloric content. They have the same osmolarity, same pH. Okay, liquids empty out faster, followed by solids, then by fats. Again, assuming the same amount of calories. This has been kind of an interesting perspective. And so people have thought, well, it's an interesting observation, not perspective, but people have wondered, how in the world did these guys empty out slower? And it wasn't entirely clear, but I'll give you some potential ideas as to how these guys empty out slower compared to the liquids versus the solids. First of all, one of the ideas about fats that we know for sure is that many of our fats that we consume will liquefy at body temperature. Give you an example, butter. You consume some butter, get it into body temperature, liquefies, not a problem. We also know that many fats do not liquefy at body temperature. They may stay semi-solid, or they can sort of be a greasy-ish, if you will. Some animal fats, for example, you consume them, they will not necessarily liquefy at body temperature. But one of the ideas here in regards to this is the theory is, well, we consume fats, both the ones that liquefy as well as the ones that do not liquefy. We consume the fats. In the tummy, they combine. In the stomach, they combine. And as a result of that, they form sort of like a semi-solid. And at this point, the semi-solid, this is now handled like the emptying of a regular solid, right? So imagine you had some of these fats that were liquefied, basically gloms on, sticks together with these fats that are more or less in their solid shape. Then you form this semi-solid that's still a bit hard to break apart. But what's interesting about the semi-solid, look, it's high calorie, and it also should have some size to it. So as a result of that, if I mentioned it, remember, we'll always have that lag phase. It's going to be dependent on the size and the calorie content. So if we have a bigger particle, it's going to make the lag phase for this guy even longer. Calorie content is elevated. Yep, lag phase for this will be even longer. So as a result of it, this probably contributes to the fats emptying out slower. Okay, so that's one theory, and it probably holds true. Here's another idea too as well. We know for sure is that when fats are emptied from the stomach and go into the duodenum, typically in the form of free fatty acids. So we'll get a little bit of fat digestion that goes along in here inside of the stomach. A bit of it got digested by the salivary lipases. So you'll have a bit of free fatty acids in here, and some of these free fatty acids would sneak out of the stomach, come here into the duodenum. So as some of these free fatty acids enter into the small intestine, now recall that the majority of the fats inside the stomach are not going to be digested up. Only a couple of them, not all of them. But as they empty out into the small intestine, what will then happen is that we induce the release of CCK, cholecystokinin, right? CCK is released. This is a hormone, and we note that CCK is super important for inducing, say, the gallbladder to release its contents. We'll get the pyloric sphincter, the sphincter of Oddi to relax. We'll talk about that a little bit later. And we could get pancreatic secretions. We could also get biliary secretions. But this hormone also goes into the bloodstream and influences a variety of things like satiety. One of the things that CCK does as well, besides those other ones that I mentioned, is that CCK decreases the gastric emptying rate. And the way it does it is by it mainly makes this pyloric sphincter, this guy here, makes it clamp down nice and tight. So this is probably another super important parameter that will basically slow down the emptying of fats. And as you can imagine, when you have fats in your tummy, they're going to stay in there for a longer period of time. And that's an advantage to you and me, because if we want to feel satiated for a longer period of time, it's probably a good idea to have the fats in our tummy, because, well, they'll be in there and we'll be inducing that distension of the stomach, and you'll feel that. You'll get the sensation of fullness, and that's probably a really, really good thing for you and me. One more thing to consider. So we got through our liquids, we got through our solids, we got through our fats. Finally, this thing that I'm going to call non-digestible solids. What are among the non-digestible solids that you and I consume? Most common one, cellulose. That's the most common one. We often refer to this as non-nutritive debris. This empties out last. And the time in which it empties last is during the fasted motor period. Remember that I told you that the fasting motor period is made up of, I misspelled period, there we go, is made up of these three phases. Remember that? Phase 1, phase 2, phase number 3. And then phase number 3 was the one where we have those very, very strong rhythmic contractions, last for about 5 minutes or so. But remember, during phase 3 is that the pyloric sphincter is opened. And as a result of that, you can then manage to empty out a lot of this non-nutritive debris, because this thing is nice and big. It's not going to be tiny opening inside of it. It only allows these guys about 1 millimeter in diameter and smaller to empty. But now we can get these bigger particles to come out. So the particles that are going to be coming out are on the order of about, like, say, 3 to 7 millimeters in diameter. And of course, remember, we got this idea that you and I are doing this fasted motor period because the tummy or your body thinks, hey, I'm starving, I got to get rid of this stuff, put it into the small intestine, so that way if there's any nutritive value to it, I could go ahead and absorb those calories. So that's the reason why we'll go ahead and do this non-digestible solid emptying during the very end, because it's the biggest thing that comes out. The stomach probably has a hard time breaking down cellulose because of the types of bonds within cellulose. They're rather strong. They're not as easily broken apart using the digestive enzymes that are secreted by the stomach. So that's why the non-nutritive debris can stay within its shape. It doesn't really get busted apart too easily. It's surprising. You know, you could even get big particles to come out of the stomach during this period of time. In the literature, it's been reported that sometimes things that are as big as 2 centimeters in diameter can come out. Now, the problem with this is that if you have an occasion of a patient who ate something that's really sharp, like this, a pen cap, like something like this, or maybe they chewed up a pen cap and you know, this is long. This is about 1 inch long, but you know, the size of this is probably about a centimeter and a half in diameter. But imagine if this thing had jaggedy edges. If this thing ends up inside the small intestine, you can perforate the small intestine. Well, the stomach could get perforated too, but boy, that small intestine has got some very thin walls. It certainly doesn't seem to be as robust compared to the stomachs. And so the danger about these big things emptying out of the stomach during phase number 3 is that you can potentially get things that can perforate the stomach. That's the danger about it. And we would never really want that to happen. All right. So non-nutritive debris, cellulose, basically empties out of the stomach during this particular time. All right. Now, one last thing to consider. One last thing. Now, sometimes people will eat things that they're not supposed to eat. Remember how mom tells you, don't eat your gum. Don't swallow your gum. Go ahead and chew your gum, but spit it out, put it in the garbage. You're never supposed to eat your gum, because mom told us that the stuff will stay inside of our stomach for like 2 years or so. And I have no idea how moms know this, but you know what? Our moms are way smarter than we are, so let's listen to our moms. They know exactly what they're talking about. I think all of them took gastrointestinal physiology sometime in their life. I don't remember teaching them, but somehow they know. Anyways, here's the point. Sometimes things remain in the stomach, and when you keep things inside the stomach, what'll happen is that these contents will eventually get coated with a variety of secretions and can even begin to stick together, glom onto other pieces of material within inside the stomach. And what happens is that we would form these things that are referred to as bezoars. And bezoars are these objects, big balls / spheres of unemptied material within the stomach. Don't worry, I'm going to get back to the gum in a moment. The typical bezoars that have been well described, whether in animal models or in human models, they seem to have a common, what would the word I'm searching for, common nucleus or common substance that they're made out of. So for example, you can sometimes have these bezoars that are made out of hair. You may wonder, why would a person have a bezoar that's made up out of hair? They refer to these guys as trichobezoars. The reason why sometimes people have these bezoars made out of hair is that folks will sometimes, as surprising as it sounds, they'll chew on their hair, especially as a nervous habit. And this has been described, of course, in girls, because sometimes girls will chew on their hair. Not to say that all women do this, but there's been examples mentioned in the literature. Girls will chew on their hair, they'll swallow some of it down, and the bezoars will start to form, and it just remains in the stomach. And it's this big old ball of hair, if you will, that stays in there. Now, it's not softball size, okay? It's not gigantic. It'll probably be about the size, obviously, it's going to be a lot bigger than 2 centimeters in diameter, right? Because it's not going to empty out. Sometimes you get bezoars that are formed from medication. And the part of the medication that it forms from is this gelatinous coat that is typically surrounding pills. In the old days, ask your parents about this, how sometimes pills would be formed in these things called capsules, and they'd have these gelatinous capsules that surround all these tiny little beads, and it has the medicine in it. And the medication type of bezoar, we refer to these as pharma bezoars. Bezoars, there we go. Pharma bezoars. And it's really the gelatinous gelatin stuff that just is kind of sticky and it'll stay inside the stomach. It's on occasion hard to break down. It's actually an advantage in terms of medication because sometimes it allows us to put a medication in the tummy that doesn't get broken apart too quickly, so that it doesn't get broken apart as you're swallowing it and stick to the interior of your esophagus. But then as you were eventually beginning to break it down, that little gelatinous part stays within the stomach. It can potentially form pharma bezoars. Then finally, another type of bezoar that forms, I think this is kind of interesting to note, that it can form from plant material, veggies, fiber. One of the notable ones is from persimmons. We love persimmons in our family. My kids eat them. I like them. I'm not as much of a huge persimmon type of a person. The names of these will often refer to them. If they're plant material, we refer to them as phytobezoars. I don't recall what the name is given to the ones that are made out of persimmons, but phytobezoars are the ones made out of plant material. Persimmons are kind of sticky too, by the way. So if you eat a bunch of this, they'll kind of stick together, form this little ball of stuff in the stomach. Most patients are asymptomatic of this, the bezoars, because they won't affect digestive processes, breaking down food stuff. It doesn't affect gastric emptying. It doesn't affect any of the secretions that come out of the stomach, so it's not a big deal for people form these. Very, very low incidence too, by the way. So don't think that, oh my goodness, I eat a lot of persimmons and hair and I take a lot of medication, so triple play, right? Don't think, okay, you're going to be at risk of getting these bezoars. But they do happen, and sometimes people get them discovered if they go and see their gastroenterologist and they get scoped out, and the doc will see it and they'll probably remove it. But in general, it's not usually a big deal to have the bezoars. You'll even see this in other animal models. For example, cows can get these bezoars. Horses can get them as well. And worry about getting them in animals because like cows, when they graze, they'll graze really low to the ground, and they eat everything too, by the way. They'll eat like metal or sometimes tiny chunks of like barbed wire. Not tons, okay? Just on occasion they can. If that ends up in the stomach, boy, it could perforate inside the cow, and that's not a good thing. So bezoars are interesting. We can form them. Now, what about the gum? Well, to my knowledge, I have no idea how long gum stays in the stomach, but hey, to my knowledge, gum is not digestible. We don't really have the capacity to break it apart. And I would bet, and I'm a betting man here, right? I'm just sort of guessing here. I wouldn't doubt that it could potentially form a bezoar if you have some of this really fibrous stuff like hair or even some vegetable fibers inside your stomach. So like mom said, don't swallow your gum, all right? Eat good stuff instead. Gum is not meant to be swallowed. Okay, let's move on here. Talk about our last topic in regards to gastric emptying. And this is kind of an interesting thing that occurs in some patients where we have these disorders of gastric emptying. And by the way, if a person forms a bezoar in their tummy, that doesn't mean that they're having a disorder of gastric emptying. It's just that, you know, if we're glomming up this stuff together inside the tummy, it just isn't going to empty out very easily. And it's not a disorder. It's just something that happens naturally. Disorders of gastric emptying, on the other hand, this can arise from a variety of things. So, for example, and typically the word that we use for a problem with gastric emptying, we refer to it as gastroparesis. Gastroparesis. Gastroparesis is sort of a universal term that refers to a problem, a lack of stomach contractions. Now remember, in order for us to do gastric emptying over here, we had to have those peristaltic contractions are pushing things down, getting the retropulsion, and then, particulating everything up. But really, it's the stomach contractions that eventually push stuff out through that pyloric sphincter. In gastroparesis, we have some problem in general with the stomach contractions. The first type of gastroparesis that arises, we just don't know how it happens, and we don't know why it occurs, but we're going to refer to it as idiopathic gastroparesis. Very, very rare. Very, very rare. In patients who have this, it arises suddenly, and sometimes it arises with viral slash sort of this gastroenteritis. This virally caused gastroenteritis. So don't worry. If you happen to get sort of a viral infection that affects your tummy, that doesn't mean that you're going to get gastroparesis. But some of the cases that have been mentioned in the literature, you'd hear about a patient, all of a sudden they have non-functional stomach emptying here, right? They get this very, very abnormal gastric emptying. And it occurs after a viral infection. Unclear why it arose. Not common. You can sometimes even get gastroparesis that arises after stomach surgery. I don't know the statistics in regards to how common that is, but it is known that that occurs. And you can imagine if you do stomach surgery, you're going to be doing quite a bit of pushing and shoving of the tissue of the stomach. You could probably damage perhaps the myenteric plexus, submucosal plexus, or even say the extrinsic pathways going into the tummy, and therefore going to affect the gastric emptying. Finally, the last one to consider is this one that's referred to as diabetic gastroparesis. In the case of diabetic gastroparesis, what occurs there is that in type 1 diabetics, for example, there's often neuronal damage. And this neuronal damage, by the way, it can be kind of global. It can affect peripheral neurons. It can affect, like, say, the retina. One of the common things that you would see for people who have very, very severe diabetes, type 1 diabetes, is that their eyesight is being affected. And basically it's because the elevated plasma glucose is causing this neuropathies. And so remember, back when we were learning all about our gastrointestinal tract, it happens to have its own nervous tract, right? Its own brain. In the case of type 1 diabetics, these individuals can have neuropathies that, I apologize for this camera shaking too much, that basically cause GI neuronal dysfunction. Now, whether the dysfunction is occurring at the level of the autonomic nervous system or at the level of the intrinsic neurons, remember the myenteric plexus, submucosal plexus, it's not necessarily clear. But what will happen in these folks is that you'll just see really abnormal contractions, peristaltic contractions within the stomach, among other places too, by the way. They'll have abnormal peristaltic contractions even in the small intestine too as well. So they have abnormal peristalsis within the stomach over here in the the distal stomach. They have problems with controlling the pyloric sphincter as well. And so as a result of that, they have pretty much very, very slow gastric emptying. All right, so that's our basic ideas about gastric emptying. And the next really cool topic that I want to hit on, and I think we have enough time to talk about it too here on my podcast here, because I'm seeing that I'm about 35 minutes on. So I want to talk about gastric secretions, all these really cool secretions that come out of the stomach, and how they will be contributing to digestion of the food stuff, as well as for protection of the stomach as well. So the components that you see within the gastric secretions include the following. We'll see definitely lots of water. We'll see lots of ions too as well. Not a ton of ions too, by the way. Do keep in mind that this stuff is pretty much isotonic, or sometimes it's hypotonic relative to blood. You'll see mucus, and the mucus that comes out, by the way, this is a protective secretion. Don't think of it as like a ton of mucus that comes out. Think of this as a mucus secretion that pretty much will coat on the interior of the stomach. I'm going to separate this out because this is a special series of the ions, hydrochloric acid, HCl, that comes out for breaking apart bonds, really hydrolyzing bonds, not really busting the bonds, but hydrolyzing hydrogen bonds in quaternary, tertiary, and secondary structure. Digestive enzymes, and the digestive enzymes are pretty much going to be targeting proteins. The main one is this guy called pepsinogen. Pepsinogen, by the way, we'll talk about in just a moment. That's a precursor enzyme. And finally, you could get the stuff called intrinsic factor. We're not going to really talk about intrinsic factor too much, but just to give us a really quick idea about intrinsic factor, this is important for vitamin B12 absorption, and it is going to allow the small intestine to do vitamin B12 absorption, but it's coming out of the stomach. You're not going to do the B12 absorption in the stomach, but it's within the small intestine. So we need this guy so we could have proper B12 absorption. That doesn't look like a B. Let me fix that again. B12 absorption. I apologize for my writing. I'm not so used to writing on this pad here. Anyways, I want to focus in on a bit of the morphology first, and then talk about the hydrochloric acid secretion in a moment. It's kind of interesting, historically speaking. People knew of hydrochloric acid secretion within the stomach. I mean, this is something that people knew of way back in the 17th century. You know, we're talking about 1600s, if you will. And lots of folks thought, well, keep this in mind. They didn't know more about the morphology yet, or the cellular physiology yet. They said, they knew that we have salivary glands. Back then, they also knew of the existence of the pancreas, and they also knew about the ideas about fermentation, but they weren't entirely sure exactly where this acid was coming from. And it took until basically, like, I don't know, 150, 200 years later, and people figured it out. No, the stomach has the capacity to secrete acid. Let's take a look at the morphology and see how this is all built. If we were to take a look at the stomach sort of from a lateral perspective and then cut through the layers, but we're going to focus in on the mucosa, and we're in the stomach and we're only looking at the mucosa, what we'd find, of course, is here's the lumen of the stomach over here like that. So you imagine that's where all the food stuff is. Here's a bunch of epithelial cells that are lining the lumen. And these epithelial cells too, by the way, are going to get replaced quite a bit because they get destroyed quite easily by the stomach acid as well as by the digestive enzymes. We'd find that there's these really deep invaginations of the mucosal epithelium like this. So here's the epithelial cells going down. And the term that we use for these epithelial cells, we often refer to these guys as surface mucus cells. Pay attention to the spelling of mucus. Mucus right over there, M-U-C-O-U-S, that's used as an adjective. They are capable of secreting mucus, and they're the ones that line the stomach right next to the lumen. Okay, you see the structure over here? I'm not going to draw all the cells surrounding it because it's going to get to be a little bit of a pain. This particular guy is referred to as a gastric pit. And so you can see there's the opening of the gastric pit, but it's a deep invagination. Remember, this is all over here. All this. This is all here within our mucosa. So we have lamina propria sitting out over here. Gastric pit has some of these little branches that come off of it. And what we find is that there's some of these cells that are lining kind of like the neck region of the gastric pit. So they're given the name, how unimaginative, neck mucus cells. What happens is that over the period of about a day to 3 days or so, you and I, we shed these surface mucus cells because they get destroyed. I mean, after all, you're eating food, the acid and the digestive enzymes break these apart, these then get shed, and then the neck mucus cells, these guys will then migrate out this direction to replace them. Surface mucus cells, they'll produce a mucus secretion, and the mucus secretion just sits right along here, right there. It's a protective layer, and it, well, prevents over destruction of the stomach by the acid and all the digestive enzymes. So it's important that these guys are able to produce that mucus. But again, they get killed pretty quick. Replace them every 1 to 3 days or so by the neck mucus cells. So the neck mucus cells, again, migrate out. We look a little bit deeper. What we'd find then is another important cell. I'm going to draw them looking kind of triangular. This is one of my favorite cells in the world, this particular guy. And he is an acid secreting cell. Refer to this guy here as the parietal cell. Really, really neat cell, how that guy works. Go a little bit deeper, we can see another cell sitting over here like that. I'm going to draw him in green. He doesn't stain green too, by the way. Parietal cells, when I look at them under the scope, I tend to see them looking kind of like a pinkish color, and I see all these little pink granules inside of them. This guy also stains kind of like a pinkish red too as well, but it has a different morphology. If I recall correctly, I think they pick up a little bit of a purpley blue color, but these are super easy to see, the parietal cells. Anyways, I'm digressing. This guy down over here is referred to as a chief cell. So we would have lots of parietal cells sitting over here, and then we begin to see the chief cells as we get more towards the bottom of the gastric pit. We don't see a ton of chief cells towards the top. Parietal cells, we'll see them from middle and then throughout, and then mainly chief cells down over here. And then we see some other guys too as well. So for example, we'd see a little dude sitting right over here. I'm going to shade him in a little bit. And this guy is a G cell. If you remember, the G cell is going to be producing gastrin. And then I put another guy sitting just outside of the gastric pit, sitting right over there. Do I have a nice little color I could put him in? No, I don't. That's okay. I'll try to color him in blue. I don't know if the blue is going to show up too well. This guy here is an enterochromaffin-like cell. And he is responsible for producing histamine. So there's the G cell. This little dude here produces gastrin. ECL cells is the one that's going to be producing histamine. Gastric pits, we see lots and lots of them sitting within the stomach. You see within the fundic region, through the body. You can even see a bunch of them in the antrum. So what's the purpose of these guys? What do we have to have them make? Well, here's the secretions. First of all, the first most important secretion in my estimation, the one that you're producing all the time, is mucus. The mucus secretion, which is coming out of the surface mucus cells. The purpose of this is simply it's a protective layer. And you can think of it as just sort of sitting there right up against the surface here. I'll just sort of draw this little greenish here like that. This greenish layer here, thin layer. Protective layer. So if there's acid content in here, it presumably won't penetrate too much to damage the mucus cells. But again, remember, we do kill off those mucus cells. Have to replace them. The mucus secretions, protective. It's made up of mucins. And you'll also find that there is a thin layer of bicarbonate, HCO3-, that is just underneath it. And the way it's going to look is kind of like this. So imagine we have our mucus cells sitting here like this. There's a mucus cell, put a little tight junction over there. Here's another mucus cell, another tight junction over here. Here's the lumen sitting there like that. The mucus would be laying just like this, sitting here on the top, as such, like that. And then you'll see the bicarb, an aqueous bicarb layer sitting over here. So there's a lot of bicarb sitting here. So if hydrochloric acid manages to penetrate through the mucus, bump into the bicarb, hopefully that's going to be able to neutralize that. All right, what else do we see? What else are we going to be producing? The next important secretion comes out of this little guy. That is hydrochloric acid, HCl. And the purpose of hydrochloric acid that's being produced by the parietal cells is that you can think of it as being a digestive type of a secretion, but do keep in mind that this acid is not breaking apart covalent bonds. It is digestive in the sense that it neutralizes. It's going to denature, not neutralizes. It denatures hydrogen bonds in proteins. And the reason why you want the hydrogen bonds broken apart in the proteins is that that will allow you to get the quaternary, tertiary, secondary structures, they'll be gone. and then that'll linearize the polypeptides. When you linearize the proteins into these long chains, then it's easier for us to break them apart. The digestive enzymes can get in there, easily break things apart. So that's the significance about why we want to go ahead and linearize things by denaturing those hydrogen bonds. Again, the parietal cells are going to be producing them. You only want to produce hydrochloric acid when it's absolutely necessary, because frankly, I like to say that hydrochloric acid is this metabolically expensive secretion that comes out of our parietal cells. The next secretion to consider, number 3, is going to be digestive enzymes. Already alluded to that. Pepsinogen. And what pepsinogen is a digestive secretion that's coming out of the little chief cell, that guy right there. And this is a precursor digestive enzyme. Precursor. And this guy is going to be targeting dietary proteins. What's interesting is that you'll see inside the chief cells, if you were to look at them under light microscopy, you'd see a whole ton of these little vesicles that are going to be containing the pepsinogen, just holding on to it. And then when the stimulus comes that's appropriate, then bang, you go ahead and secrete that stuff out. So that's what pepsinogen is all about. And pepsinogen eventually is going to get converted into the active form of the digestive enzyme. We'll talk about that in a moment. We'll see how that's going to be working. All right. Then finally, the last secretion, and this is not indicated on here, okay? Because all of these secretions, if I'm calling them gastric secretions, these are exocrine secretions, right? These are all going out of the body. They're all going into the lumen of the stomach. They're exocrine secretions. The last important secretion is an endocrine secretion. Endocrine/paracrine secretions. Those are going to be gastrin and histamine. The significance about gastrin and histamine is that we're going to use those two endocrine secretions, paracrine secretions, for really controlling the stomach secretions. That's the purpose of them. All right. Okay. Let's see this. Let's look at our guy over here, the parietal cell. Let's see how that guy is regulated. Because as I mentioned, we need to only secrete hydrochloric acid only when it's absolutely necessary. You never really want to turn on hydrochloric acid secretion when you don't have any food stuff inside of the stomach, because frankly, I like to say that the hydrochloric acid secretion is metabolically expensive. And you'll see why in just a moment. We're going to see two different states of our parietal cell. And the parietal cell happens to have an apical side over here where my pen is pointing. There's the apical side of the cell. There's the basolateral side. This is facing where the bloodstream is. The apical side is where we're going to be secreting out the hydrochloric acid. And this is a parietal cell that is at rest. This is prior to you and me being exposed to any food stimuli. And it looks like that at the apical end, which is over here at the top, right? There's the apical end. At the apical end, the secretory canals are small. Sometimes people like to say that they're collapsed in. I'll be honest with you. I've tried to look at it under light microscopy. I can't tell, to be perfectly honest with you. So I'm going to trust whatever the literature says. And if they say it's collapsed, fine, so be it. Secretory canals are small, not really elongated, but more importantly, what you'd find is that there's a whole bunch of these little vesicles that are over here at the apical end, right over here, towards this end. Lots and lots of vesicles. I'm going to draw one of these vesicles. I'm going to exaggerate it. I'm going to draw a vesicle with a little transporter there, and then another guy, which is a channel, sitting there like that. Okay, so we have a transporter and a channel. You'll see how this works out. I know you can't quite see it so much on this camera, but you'll see how it works. These guys are not producing very much acid at all, because the majority of these vesicles contain the secretory machinery, if you will. That's important for hydrochloric acid secretion. We'll talk about them again. We'll talk about them. So Lots of these vesicles at the apical end. Lots of vesicles. I'm not spelling vesicles correctly. Vesicles at the apical end. All right. So this is in the rested state. I don't know why I put that little asterisk there. You'll have sort of this background secretion too, by the way. When you are, when you're in the absence of food stimuli, within the stomach here, there is actually some background secretion that's coming out. Tiny, tiny volume too, by the way. Not much acid in it. The secretions that are coming out are probably coming out of the mucus cells too, by the way. It's mainly mucus, a bit of bicarbonate. Again, low volume in there. And you could think of this background secretion as more of a maintenance secretion. And so the background secretion is occurring here in the rested state. Now, if on the other hand, we go into a stimulated state. So I wanted to put rested right over there. Let me put this over here. Rested state. There we go. Should have started off like that. Oh well. Stimulated state. We'll see a dramatic change that occurs within this guy. You'll see it primarily here at the apical end. Now, what's interesting is whenever you get a vesicle to fuse with a membrane, and let's just pretend we're not even looking at a parietal cell for a moment here, but if you were to have a vesicle, so imagine I have a cell here sitting like this, and then I have a vesicle like this guy. There's a vesicle, and this guy decides to fuse with the plasma membrane. What will happen is that as the vesicle fuses with the membrane, the plasma membrane, it too is adding on additional membrane. So there it is. You can't see it in red. You'll be able to see it a little bit better when you get the downloaded notes. There's the vesicle. It added a little bit more membrane. If we have a lot of these vesicles fusing with the membrane, you can imagine the cell would grow bigger and bigger and bigger, right? Because you're adding more and more membrane. But as opposed to doing that, as opposed to making the cell get bigger in volume because we're adding so much membrane, one of the other things that the cell can do is it can begin to fold the membrane to account for that excess membrane that's being added. So we'll still maintain the rough size and shape of the cell, but now as we add these vesicles, here's the red. You know, the red is representing all these vesicles that we fuse to the membrane. This is how we can account for that additional membrane that's then added to the apical end by doing that. So if we had all these little vesicles right over here and getting them to add themselves, again, to the plasma membrane, adding them up without increasing the cell size, this is what you would want to do. And sure enough, in the stimulated state, the parietal cell starts to look like this. And let me draw it in red here. Like that, so we just have some consistency. I'm going to draw a little bit bigger. We put all this membrane in here like this, lots of folds in it, and they will then basically form these things called secretory canals. So there's our secretory canals at the apical membrane. These secretory canals, secretory canals, are now elongated. Because remember, these vesicles were fusing with the membrane. And more importantly, as these vesicles are fusing with the membrane, they're sticking onto the membrane all the machinery that's necessary for acid secretion. I'm going to draw these little black dots. We'll talk about them in just a moment. These little black dots and probably these little channels here. I'll just draw 2 channels because I don't have enough room stuck in there. Secretory canals elongated. The hydrochloric acid secreting machinery. Machinery is also added to the plasma membrane. Now, during the stimulated state, this is going to occur after you basically get exposed to a food stimulus. And what's really remarkable is that it happens quickly, super, super fast. That response is robust. And it's promoted by the following. So, for example, let's see, food stimuli that you like say, okay, hold on, let me step back for a minute. Food stimuli induce the response, And the way the response is induced is that you can be like, say, seeing food. You could also be smelling food. You could be tasting food. It also occurs after you're eating food, and even as the food is in the stomach. And we're going to talk about all these different phases in response to these particular stimuli. So it's going to be inducing this response. It's remarkable. All you have to do is talk about food stuff, and then kapow, you get these guys stuck there in the apical membrane. It's absolutely remarkable. Let's see how those transporters are working too, by the way. How are we going to get the hydrochloric acid? Now remember, I started off saying to you, you and I don't want to produce acid when it's absolutely not required. Because if we produce acid, it's sort of metabolically expensive. And the metabolic cost, if you will, is an effect on our blood pH. Because you'll see in a moment how when you and I are producing acid, we have to run a particular chemical reaction. And as we run this chemical reaction, it will then change our plasma pH. So let's see how this is working. We're going to draw ourselves a parietal cell. And we're going to draw a really ugly looking parietal cell because we need lots and lots of room to draw things on here. So this is supposed to be a secretory canal, this little short fat thing, but that's okay. Let's put ourselves a little channel sitting over here like this. And then we'll put right over here a little transporter sitting there as such. And then we'll put another channel sitting here as so. And I will go ahead and kind of close this off, if you will. Put another parietal cell, put a nice tight junction over there. And so here's our little parietal cell sitting next to it like there. So here's a couple parietal cell. This is the way it really should look like. This is our cartoonish looking parietal cell. Bloodstream sitting down over here. I apologize if you hear my dog. She might start barking. She's cruising around and she's looking for food. Anyways, let's see how this is working. Here's our blood. The blood flow increases too, by the way, to the stomach in response to food stimuli. We get this increase in flow. It's parasympathetically mediated, which is pretty neat. Blood's coming through. And as the blood is flowing, some carbon dioxide comes out. Carbon dioxide will then enter into the parietal cell. And the carbon dioxide will then react with water like this. So if you remember, if we react carbon dioxide with water, what's going to happen is that you'll form carbonic acid, H2CO3. And this will then spontaneously dissociate into a proton plus bicarbonate HCO3 minus. Okay, so what we want is this guy, the proton. The bicarbonate, we don't want it to remain in the reaction because you remember this back in chemistry, how if we draw the double-headed arrows, we know that this is a reversible reaction. And so that means if say the end product starts to build up, then we can't run this reaction towards the right. I know it's drawn up and down, but you know, the chemical reaction would be going to the right like this. I hope you understand what I'm getting at. We need to remove this. And we also need to remove this so we can continue to run the reaction. And if this builds up, the reaction slows down. So imagine this is running, form the carbonic acid, it dissociates. Here's what will happen as we form the proton. Proton comes out like that. And then the proton will then be pumped into the lumen of the stomach, of the gastric pit really. And then eventually makes its way out into the stomach. And there it is, there's our proton. There it is, H+. I kind of made that an ugly looking proton. Sorry, it turned out to be a hairy H, but that's all right. There's our proton, boom, like that. The proton is being moved by a proton pump. And this particular proton pump is pretty interesting because what it does is that as it's moving a proton out of the cell, it will simultaneously move a potassium into the cell like this. But the potassium presumably will then flow out through the apical membrane and kind of do this little circle loop thing here. You see that? This proton pump moves a proton out, moves a potassium in. So there, we took the proton out. But what about this guy? What about this bicarb? Well, we think that the way that the bicarb is handled is through our ubiquitous bicarbonate chloride antiporters. Right? We have our typical bicarbonate chloride antiporters, and what this guy will do is that it will take the bicarb, HCO3 minus, and it will then move it into the blood like this, HCO3 minus, HCO3 minus. There it is. There's a bicarb that's taken out. And so the significance about this is that this allows us to continue the reaction so we can continue to make the proton, because we need that proton for hydrochloric acid. What else is this guy moving? This bicarb transporter. Well, it also moves simultaneously chloride out of the blood into the cell, and that's what's facilitating the bicarb moving out. And then this chloride will then manage to move through a chloride channel. And there's our Cl. There it is. There's our hydrochloric acid coming out. So those are the components of the secretion. We have a chloride channel over there at the apical membrane. We have our proton pump. And this proton pump is really more of a potassium hydrogen antiporter. It's an ATPase too, by the way. And then finally we have over here at the apical end this bicarbonate chloride antiporter. I don't know the stoichiometry, by the way. I don't know if this moves out two bicarbs to 1 chloride or 1-to-1. I'm not certain about it. But the point is that this allows us to take that bicarb out and allows us to run the reaction continuous to the right. If you want to make this picture nice and pretty, you can go ahead and throw in the sodium potassium ATPase that moves in 3 sodiums and then 2, oops, I did it the wrong way. Moves in 2 potassiums, 3 sodiums out. If you want, you could do that. But here's the deal. See that bicarb? See that right there? You could see that it would basically cause the pH of your blood to rise as you produce acid. Now, changes in plasma pH, we always want to defend against that, because after all, that's something you and I will homeostatically regulate, our plasma pH. Can we account for this? Absolutely, we'll account for this. Later on, when we look at how the pancreas is working, as the pancreas produces its own exocrine secretion, its own bicarbonate secretion, it puts the proton into the blood. And it should be doing it essentially 1-to-1 for acid secretion. So for every proton coming out of the parietal cells, presumably we'll get a bicarb coming out of the pancreas. And for every bicarb put in by the parietal cell into the blood, this guy right over there, that gets accounted for or neutralized, if you will, by the protons coming out of the pancreas. This is the reason why I like to say, hey, look, you and I, when we're going to be doing this particular type of secretion, we only want to do it when it's absolutely necessary. We don't want to overproduce acid. We don't ever want to overproduce bicarb in other places unless it's absolutely necessary, because we can have potentially these acid-base challenges, if you will. As these things are coming out, hydrochloric acid's coming out. What will also follow, because it's pulling osmotically, water. That's what is also going to come out. So here comes our water coming across like that. So that is how you and I get our water coming in there. Okay. Now, is there anything else that comes out? Well, let's see. Let's see what else could be potentially coming out. If we were to take a look at our secretory rates, remember how we did some of the secretory rates, we were comparing like salivary secretions, you know, during a stimulated state versus a basal secretion state. We find that the ionic composition, that changes. It changes with secretory rate. Secretory rate. Let's see how it's going to be working. As I mentioned to you, during basal secretions, one of the things that we find is that there is very, very little, absolutely none, pretty much, low to none hydrochloric acid within the secretions. Furthermore, what we find is that if you look at the sodium content, and if you take a look at, like, say, the potassium content, and, like, say, the chloride content, pretty much like plasma, almost like blood concentrations. So the concentrations of sodium, potassium, chloride within our gastric secretion, just like blood. So that means that these are probably coming out of the blood somehow. Notice that I didn't give you really a mechanism by how they're coming across. Finally, isotonic. This secretion, relatively isotonic to the plasma, so it's going to have roughly the same osmolarity, about 300 milliosmol or so. A tiny bit of bicarb, and probably that bicarbonate is coming out of the mucus cells. Remember, a lot of mucus in there, and it's coming out of the those mucus cells, surface mucus cells. We refer to this secretion as the non-parietal secretions, because again, most of these secretions are more of a maintenance type of a secretion, something that is really coming out of, like, say, the mucus cells, just maintaining the integrity of the stomach. Not a digestive secretion at all. The non-parietal secretion, that's what we're going to call it there, a non-parietal secretion. On the other hand, exposure to a food stimulus, what'll happen is now we get into our stimulated state. Stimulated state secretions. And here's the interesting thing that happens there. Is in the stimulated state, of course, lots of hydrochloric acid, HCl, lots of hydrochloric acid in there. And what we also see is that in regards to the sodium content in gastric secretions is pretty much the same as the blood. With regards to the chloride content increases relative to the blood. I mean, it kind of makes sense because, well, after all, it's coming in as part of hydrochloric acid, right? And the other thing that we find is that we'll see that the volume is big. Volume is large. Okay. So, excuse me. I screwed up on the sodium content. Sorry. Sodium content. I'm sorry. It's not the same as blood. Totally wrong. The sodium content in it actually drops. Kind of a weird one. We don't quite understand it. I'm going to show it to you in a moment. Volume is large. We also find that this solution is slightly hypotonic. In other words, it has a lot more water content in it. Now, that's really important because when you and I are digesting foodstuff in the stomach, we want to also be able to dilute the contents in there. Remember how I said to you that with gastric emptying, we don't want the solution coming out basically hypertonic. We want it to be closer to isotonicity as much as possible. Well, if you're going to dilute something, you have to add a solution that's hypotonic, more watery. Well, there it is right there. The hypotonic solution will help dilute the contents within the stomach. So that's the reason why we want it to look like this. If we were to represent the ion concentrations, remember this is all relative to blood. So if we say, all right, here's the sodium content that you would see in the blood. There is sodium right there. And if we look at potassium, there's potassium content. Chloride, somewhere over here like that, chloride. And then bicarb. We're not going to worry about bicarb because bicarb is kind of meaningless, if you will. What we would find is that with respect to the sodium content does this type of deal. So here's sodium. At low secretory rates, whoops, I forgot to show this to you. So this is the ion concentration. This is blood over here. This is stomach secretions. Exocrine secretions. So here's at our low flow rates. This is at our high flow rates. Low flow, right? There we go. High flow rates. Remember, high flow rate, that's when you're being stimulated by food stuff. Here's what sodium does. Starts off over here, and then as you get to high flow rates, falls off like that. Bonk, like that. In contrast, if you were to take a look at, like, say, the potassium concentration, not a ton of potassium in the blood. So it, too, doesn't really change appreciably. There's our potassium content. Okay, plus sodium over here. Let me indicate it. Let me put the sodium like this. There's the little sodium label that goes over there. Chloride content goes elevated. Chloride goes like this. Starts to come up like that. Oops, I should use a different color. Let me use blue. Apologize. Blue. There's our chloride content. It's chloride. So there's our chloride. Like that. And then protons. Hey, you know what? We don't have a ton of proton floating around in the blood. I mean, the blood is pretty basic, 7.4, pH 7.4. So you know at low flow rates, remember how I said you don't have very much acidity in there? So there shouldn't be very much protons in there. But as we start to increase our flow rates, here's what happens to hydrogen levels. Hydrogen ion, there it is. H plus, like that. The one that's the conundrum is this guy, that sodium content. It's unclear how that's working. I mean, the model that I just presented to you, the way that we're doing the secretions, doesn't quite explain it. Can't be entirely sure exactly how this is working, but needless to say, the sodium content falls. More importantly, hydrochloric content, hydrochloric acid increases, HCl. Potassium content stays relatively the same. All right. Okay. Last but not least, hey, you've been sticking it out, approaching an hour and a half, perfect timing. Gives you plenty to talk about over Thanksgiving. My goodness, as you're chomping down on that food and eating your whatever it is, your turkey or your tofurkey, right? You could be talking about these secretions that are going on in your tummy. It makes for a wonderful discussion over Thanksgiving. Trust me, try it. I don't think anybody will laugh. I think people will be fascinated by it. The question, of course, is how do we control this? The control of our gastric secretions. Let's talk about our phases. The very first phase. Now remember I said to you, hey, we could get our secretions. Where did it go? I said that basically here in our previous food stimuli, right? Food stimuli. Talking about food, smelling food, seeing food, tasting food, eating food, hearing food. I mean, you know, if you're hearing that if you have super hearing, you could hear the turkey cooking in the oven. I don't know how does that sound? Or you're hearing people cooking, and it could actually get you to secrete acid. I know your salivary secretions will be going, but yeah, you could start to go ahead and induce these gastric secretions. So the very first phase we're going to refer to as the cephalic phase of gastric secretions. And what occurs there is that pretty much you're having the stimuli received by the head. Cephalic refers to head. So the stimuli are, say, the sight of food, smell, taste of food, talking about food, thinking about food, hearing food. I don't know, feeling food. I don't know if you could say feeling food. None of us really like feel our food. I don't know. Maybe you could feel your food, touch it, squeeze your hamburger. Maybe you could probably get like acid secretion. Anyways, cephalic phase. And apparently this guy here is mediated by two things. Number one, or A, vagal, SNS input. Very, very strongly induced. We know that this is stimulatory. So when you have this particular stimuli occurring, vagal afferents, vagal efferents, parasympathetic nervous system. You guys should have caught me on that. PNS output to the stomach increases. We'll see how that's going to work in a moment. Second one, gastrin. You get a very strong gastrin secretion, especially as you start to get some of that food stuff coming in. Oh, let me step back for a moment. Even in the absence of the food stuff getting into the stomach, it appears that you get this rise in your plasma gastrin that comes in. Cephalic phase too, by the way, it can be. So let's see, what's the term I'm going to use? I'm going to use negative feedback. You can get negative feedback when the stomach pH drops. In other words, as the stomach gets more and more acidic, you can essentially inhibit the cephalic phase. I'm not talking about inhibit the cephalic phase to the point where it becomes zero, but it begins to drop a bit. Let me get a little holder over here. Put my non-complete Rubik's Cube there because I don't have anything else sitting here on my desk. All right. How's this working? The mechanism is a little bit complex, and follow me along if you can. So we're going to try it like this. Here's the stimuli. Sight of food, smell of food, whatever, taste, chewing on food, feeling it. Okay, this is essentially higher order input, right? This is something that you're detecting, higher order cortical input, right? And what occurs is that some of the output will then go presumably into the brain stem. So we're now getting a little bit further back in the head, getting to the brain stem. And what will then occur within the brain stem, presumably, we're going to get into the motor efferents for the parasympathetic side. So dorsal motor nucleus, the 10th cranial nerve, and also nucleus ambiguus that we're hitting on. The output comes out like this, and here's how it's going to work. Preganglionic neuron, so here's PNS. Postganglionic neuron, also of PNS, right? So preganglionic, postganglionic, this is a parasympathetic pathway. And what occurs, this is the wacky thing. This is the wacky thing that's not entirely clear. Is that there is some sort of a neuron that is actually inhibitory, okay? And it's inhibitory upon this enteroendocrine motor efferent that is controlling a G cell. So here's a G cell sitting over here like this. So here's a G cell like that. And this guy, of course, produces gastrin. And then the gastrin goes into the bloodstream. Okay, so enteroendocrine efferent. Remember, those are one of those motor efferents that's part of the enteric nervous system, one of those intrinsic neurons. This is normally stimulatory towards the G cell. So ignore for a moment, if you will, all this stuff that's covered by the pen. Just ignore that for a moment. Okay, so this enteroendocrine efferent normally activates the G cell and then it would produce gastrin, goes in the bloodstream. Okay, so we got that. Now, there is a basal background inhibition. There's some sort of an intrinsic interneuron that is inhibitory right there. So this intrinsic interneuron that's inhibitory interneuron is shutting off this enteroendocrine efferent. So as a result of that, during the non-stimulated state, you wouldn't have very much gastrin produced. You get a tiny bit of gastrin, probably, like that G34 that's coming out. Remember that guy that's important for the maintenance of the track? So not a ton. It's because this inhibitory interneuron is essentially causing the shutdown of this guy. Now, if you have sight, smell, taste, chewing, thinking, hearing food, oh my goodness, Thanksgiving's here upon us. My goodness, let's crank out that acid. We got to do something to shut off this guy. We've got to shut off this inhibitory interneuron. And then simultaneously, we also have to have some pathway that will then also activate this enteroendocrine cell. Whether we go this way or go to the G cell, who knows? But somehow we have to activate this guy so that get the gastrin secreted. But you see this pathway coming over here? I'm going to kind of highlight it in red. Kind of coming over here like this. See that there? In that pathway that we highlighted in red, we basically inhibited an inhibitory pathway. So in other words, you see this part right over here. So ignore this one to the right, but this one right here. You see that? That somehow shuts off this inhibitory interneuron. So by shutting down that inhibitory interneuron, we can then presumably activate this G cell. So it involves shutting off an inhibitory interneuron that controls an enteric and endocrine efferent. So as a result of that, G cell releases gastrin. Okay, so we're going to shut this guy off, but then at the same time we also have to turn this pathway on. See that? This pathway on. That will then turn on that enteric endocrine efferent to then cause the G cell secretion. Gastrin goes into the bloodstream. Then the gastrin, as it goes into the blood, right there, goes into the bloodstream, cruises along, talks to an ECL cell. These enterochromaffin-like cells that gets activated by gastrin. So here comes gastrin, comes in. There comes the gastrin. The ECL cell that will then secrete histamine. And the histamine will also go into the bloodstream. So there, now we have both of these guys in the bloodstream. Not going very far too, by the way. So here comes both histamine and gastrin. And then, presumably, in response to the histamine and the gastrin, that's what's going to cause those secretory vesicles to then fuse to the apical membrane of the G cell, or pardon me, of the parietal cell, not the G cell, parietal cell, because they're going to be activated by gastrin as well as histamine. Both of these guys are coming in. And as a result of that, this guy is then going to crank out hydrochloric acid. Now remember, this hydrochloric acid that comes out, even though I drew it looking like it's going into the blood, this hydrochloric acid is not. It is not going into the blood. Remember, this is going into the lumen of the tract, right? So I should have drawn it upside down instead. So maybe the lumen stomach is sitting over here. So this is a very interesting, important response. We know that we can eliminate it by simply doing a vagotomy, and it just basically shuts that down. Okay, so this is a very interesting response where we have this parasympathetic input coming in, shutting down this inhibitory interneuron, and then eventually you get the G cell to be activated. There's also another step too. One more step here. One more. Okay, what's that other step? The other step is the following. So imagine we also have the brainstem coming out. So I'll draw another brainstem. I'm just pulling them down over here too. Brainstem coming out like this. The brainstem also has, parasympathetic pathways. So here's PNS pathways, just like that, right? So here's a preganglionic fiber, preganglionic. That right over there is a postganglionic neuron right there. This too is also another postganglionic neuron. Sorry, I'm slurring. Postganglionic neurons. Here, preganglionic neuron. Post is sitting right over here. There's some evidence that suggests that perhaps the postganglionic neuron may also come along over here like this, and then also directly activate the parietal cell. Okay? So here's the effects. Remember, we have this effect that is mediated sort of through a gastrin pathway. And of course, we had to shut off this inhibitory interneuron. Then the same thing, cider smell coming in over here like this. There. Not your second brainstem, but, the other viewpoint of your brainstem. Coming in, preganglionic, parasympathetic nervous system, activating the postganglionic neuron over here. The postganglionic neuron will then probably release acetylcholine onto this guy. Acid comes out. Those are 2 steps, a neuronal path and endocrine path. And so that's happening during the cephalic phase. It's remarkable. You could block it by vagotomy. Cut that vagus nerve, shuts it down. You can even talk about food. Oh my goodness, you just simply talk about food and you get a lot of acid secretion. Furthermore, you guys, get this. You get the majority of this acid secretion in response to self-selected meals. So here we are. We're going to celebrate Thanksgiving with our loved ones, our family, our friends. And, we're thinking about those who are less fortunate than we are. And you should think about those folks who are struggling during this time because, hey, we're fortunate, right? We're able to afford going to school and probably even the good things in life. And then there's those of us who are truly struggling these days. I'm digressing anyways. But needless to say, self-selected meals, you're going to produce a lot of acid. So if you're thinking about that turkey's about coming right out of that oven, or you're thinking about that Thanksgiving pie or something great, you're going to get a lot of that acid secretion. If on the other hand, you are thinking about, oh, wow, there's something really yucky in the oven and I'm not terribly excited to eat it, you won't produce as much acid. It's really more in response to something that's particularly enjoyable to us. Two more things, two more. Here we go. Cephalic phase, gastric phase. In the gastric phase of acid secretion, what happens there is that the foodstuff is now in the stomach. And as it goes into the stomach, the thing that it does is that it causing, number one, stretch of the stomach, distension of the stomach, pushing against the sides of the stomach. There's this deformation of the stomach. It's also, as the foodstuff comes in the stomach, it's going to also cause gastrin release. And this gastrin release is occurring due to amino acids in the stomach, because as you get some of the foodstuff inside of the stomach, you're getting partial protein digestion. Amino acids are going to get released, and they're going to stimulate gastrin release. So what's going to happen in response to that? The stretch, that guy is sensed by vagal afferents. Remember, these are afferent neurons that are going to be bringing their input into the brainstem. And as that vagal afferents are then activated, it will then activate the parasympathetic reflexes. Which parasympathetic reflexes? These guys. Exactly this guy. That's it. So imagine, as opposed to saying sight, smell, taste, imagine now it's stretch in the stomach, right? You put something in the stomach in there, stretch that guy out like this. So here we go. We're going to go ahead and throw in our Thanksgiving turkey in there. There it is. You ate the whole turkey, right? There's our Thanksgiving turkey in there, plus a pie. That's my pie, right? I don't know, my pie looks a little deformed. There's your pie, Thanksgiving turkey, stretching. That looks so weird, but anyways, you get the point. Stretching out the stomach, inputs coming in, activate this pathway. We could eliminate it, do a vagotomy. You could eliminate it fairly strong. What else do we get? Well, the gastrin release, how's that working? Well, what happens in there is that in this instance, these enteroendocrine cells are going to be detecting directly the presence of the amino acids. So here's our G cell. All right, there's our G cell. Amino acids are coming in over here, stimulating the G cell. This guy will then release gastrin, and then the gastrin is then going to stimulate the enterochromaffin-like cell. He then produces histamine, and then presumably the two of them, histamine and gastrin, are going to come along and stimulate the parietal cell. Whoops, I forgot to put my parietal cell. Here's my parietal cell. And then we'll get our acid secretion, okay? Last but not least, intestinal phase. Now, in the case of the intestinal phase, the foodstuff is now in the small intestine. Food stuff is in the small intestine. And in that case, you know, it's not really necessary for you and me to continue acid secretion in the stomach, because after all, the food stuff, now chyme, really, that chyme is inside of our small intestine. No need to continue digestion or acid secretion within the stomach, right? So here's the chyme. Should really refer to it as chyme. And what occurs here is now this is an inhibitory state. What probably happens is that there are some of these cells that are sitting over here that are referred to as D cells. And what the D cell does is that it secretes somatostatin. You and I also have D cells too that are along the stomach too, within our gastric pit. And whenever you get an increase in acidity, the D cell can produce somatostatin. and presumably the acidity in here within the small intestine, right? This is the duodenum, SI, with the green chyme. That's our tiny little particulates over there. Somatostatin comes into the bloodstream. It's going to then travel a long distance to the parietal cells. And then once it gets to the parietal cells, so here's my little parietal cell sitting right over there. The parietal cell is then inhibited by somatostatin. It's going to decrease its acid secretion in response to it. And the way it's going to be working, oops, excuse me. I did that wrong. It's not going to directly inhibit the parietal cell. I apologize. I did that wrong. The somatostatin, I did that the wrong way. The somatostatin actually inhibits, I'll put it over here to the side because I don't have enough room. It inhibits the G cell. Inhibits the G cell. And as a result of that, you get a decrease in gastrin secretion. It's not like you're going to completely shut it off. You're just going to decrease the gastrin secretion. Now, this is one of the putative inhibitors, somatostatin. There's some other guys that have been mentioned, but this is the main one I think I ought to mention to you guys. Okay, so that is it in regards to our control of acid secretion. I'm going to try to get you another lecture. Let's see how it goes. I'm going to try to upload this guy here. If I don't get another lecture up for you to look at, take a peek at this. Hopefully this catches us up a little bit more and gets us ready for our upcoming midterm. The upcoming midterm is going to cover some of this material too, by the way. It is going to cover this material. You know, this is gastric emptying and our acid secretion. But it'll give you something to chew on. Hey, how do you like that, right? During the happy holidays. If I don't see you, you know, I probably won't see you. What am I talking about? I hope that you all enjoy your time with your families and that you have a really blessed and good holiday. All right, that's it, folks. Talk to you later.